If you have ever stood outside on a clear night and watched the moon rise, you may have noticed something you never thought to ask about. The moon does not rise just anywhere. It follows a path. The bright planets, when they appear, follow that same path. Venus low in the west after sunset, Jupiter higher up, the moon a few nights later sliding along the same invisible curve. None of these objects wander. They keep to a line, night after night, year after year, as if the sky itself had drawn a single track across the dark and asked everything bright enough to be noticed to stay on it. Nobody teaches this directly. Most people never learn the reason, and yet anyone who has spent enough nights under a dark sky has felt it without naming it. A sense that the planets belong to one another in some structural way, that they are not scattered randomly but arranged, like beads resting along the same length of string. They are. Our solar system is not a loose cloud of bodies drifting in every direction. It is a disk, a wide, slowly turning, almost paper-thin disk, with the sun at its center and the planets strung along rings within it. Everything we call the sky, the moon's path, the planets wandering, the band where eclipses happen, is simply this disk seen from the inside, traced edge on against the dark. And that means there is a direction most of us have never thought about at all. Not east, not west, not toward any planet or any star we can name. The direction perpendicular to the disk itself, straight up out of it, or straight down beneath it. However you choose to orient the picture, a direction so far outside our ordinary experience that almost nothing we have ever built has traveled along it in any meaningful way. No spacecraft has ever looked back at our solar system from above. No photograph exists of the planets arranged in their true pattern, seen the way you might look down at a record spinning on a turntable. We have mapped every planet individually, in extraordinary detail, from up close. But the shape of the whole, the disk itself, viewed from outside its own plane, has never been captured. Tonight, that is where we are going. Not toward a planet, and not toward a star, toward a direction. The quiet, mostly empty space above and below the place we call home, and the strange reasons it has taken this long for anyone to even consider looking there. There is no urgency in this. The direction has been waiting a very long time, and it is in no hurry now. The disk turns slowly below us, as it always has. We begin. Long before anyone had a word for the ecliptic, people were already following it. A farmer watching the moon to time planting. A priest in an ancient city marking the rising point of a particular star against the horizon, year after year, to know when a festival should fall. A child lying on their back in a field, watching 3 or 4 bright points drift slowly across the months, not understanding what they were, only that they moved together along the same general path, in a way that nothing else in the sky did. None of these people needed to know about disks or planes or angular momentum. They needed the path to be reliable, and it was. It is one of the oldest reliable things human beings have ever had access to. More reliable than weather, more reliable than rivers, more reliable, in many times and places, than the people around them. The moon would return to roughly the same line. The bright wandering stars, the planets, would drift along that same line, sometimes ahead, sometimes seeming to pause and drift backward for a while, but always within the same narrow band of sky. That band has a name now. We call it the Ecliptic, but the name came late. The path itself is older than every name ever given to it. For sailors, this path became something closer to a tool than an idea. Crossing open ocean, with no coastline in sight for weeks, the position of familiar stars along that band, rising at a known bearing, setting at a known bearing, climbing to a known height at a known hour, gave a kind of certainty that nothing else on board could offer. The ecliptic was not studied. It was used the way a path through a forest is used by someone who walks it every day without ever drawing a map of it. There is something in this worth sitting with for a moment. The same line that a sailor used to find north, the same curve a farmer used to time a harvest, the same drifting points a child watched without understanding. All of it was the disk, the whole structure of our solar system, written across the sky in a form simple enough that anyone, in any era, looking up for long enough, could learn to read it without ever being told what it was. And there is something else in that sky, fainter, that almost nobody notices at all. On a very dark night, far from any city, with the moon below the horizon, if you look toward the west shortly after sunset, or toward the east shortly before sunrise, you may see a soft, pale glow rising at an angle from the horizon. It is not the last light of sunset. It is not the first light of dawn. It does not move the way clouds move, and it does not flicker the way the edge of a city's light pollution does. It simply leans upward into the dark, faint and steady, in the shape of a wide, soft cone. Most people who have seen it never asked what it was. Many people who have spent their whole lives under dark skies have seen it without registering it as anything separate from the ordinary glow of dusk, a slightly brighter patch of sky where the sun has just gone down, nothing more. It fades quickly if you try to look at it directly. It is easiest to notice out of the corner of your eye, in the kind of unfocused glance that happens when you are not really looking for anything at all. It has a name too, the zodiacal light. It is sunlight, scattered very faintly by an enormous cloud of dust that lies along the same plane as the planets. Tiny particles, smaller than grains of sand, drifting in the space between the worlds, catching sunlight at a low angle, and sending a small fraction of it back toward Earth. The dust has been there for the entire history of the solar system, slowly replenished by collisions in the asteroid belt and comets shedding material as they pass near the sun. It lies in the plane because everything that produces it lies in the plane, and because the sun's light and the planet's gravity keep it there. To see the zodiacal light is to see the disk itself, not a diagram of it, not a model of it, the actual material lit from within, faintly visible to the naked eye on the right kind of night. There is a particular kind of memory that some people carry from childhood, of standing outside on a dark night and noticing something faint and strange in the sky that they could not explain and never asked about. A pale shape, low and slanted, gone if you looked at it too directly. Something that seemed almost like an afterimage of the sunset, except the sunset had ended an hour ago. Most children who notice something like this do not mention it to anyone. There is nothing alarming about it, nothing that calls for an explanation. It simply becomes one of the unremarked textures of a dark sky, filed away, half forgotten. Alongside the shapes of constellations, nobody bothered to name for them, and the particular quiet of a place far from any town. If that memory belongs to you, there is a chance that what you saw on some ordinary night a long time ago was the zodiacal light, the disk of the solar system, glowing faintly enough to be mistaken for nothing at all. The universe tends to be noticed before it is understood, long before anyone has the framework to explain what they are looking at. They have already looked at it, as a child watching a strange faint glow, as a sailor reading a line of stars, as anyone who has ever lain back in the dark and let their eyes follow the slow drift of the planets without asking why they all moved the same way. They were all looking at the same structure, a wide, flat disk turning slowly with the sun at its center and everything else, the planets, the moons, the dust, the faint glow after sunset, caught up in its long, patient rotation. Tonight, we are going to look at that structure more carefully than most people ever do. Not from inside it, the way every human being who has ever lived has looked at it, from outside, or as close to outside as anyone has ever managed to get. To understand why that has been so difficult, we need to go back to the very beginning, back to before the planets existed at all, back to a cloud. Picture a cloud of gas and dust far wider than anything that would eventually form from it, cold, dark, slowly turning. So slowly that across an ordinary human lifetime, the rotation would be undetectable. This is where the story of the disk begins, billions of years ago, in a region of space that no longer exists in any recognizable form. Gravity pulled inward on this cloud, as gravity always does. But the cloud was not still. It had a small amount of rotation, left over from whatever larger, slower motions had shaped the region of the galaxy it sat in. And rotation, once present, does not simply disappear. It has to go somewhere. Here is the part of the story that explains everything else. Along the axis the cloud was spinning around, call it the vertical direction. There was nothing to resist the inward pull of gravity. The cloud could collapse freely in that direction, falling straight in toward the center, unopposed. But across that axis, in the directions perpendicular to the spin, the cloud's rotation pushed back, the same way a spinning ball of dough flattens when you try to compress it from the top and bottom. The cloud's spin resisted being squeezed sideways. Material could fall toward the center, along the spin axis. It could not fall inward sideways without first losing the rotation that was holding it out. So the cloud did what spinning things under gravity tend to do. It flattened. The poles collapsed inward. The equator held its ground. What had been a roughly spherical cloud became, over time, a wide, thin disk, spinning faster as it shrank, the way a skater spins faster when pulling their arms inward, conserving the same rotation in a smaller and smaller space. At the center of that disk, the bulk of the material gathered into a single dense, hot core. That core became the sun. Around it, the remaining disk cooled. The heavier elements within it began to condense, not all at once, but slowly, into solid grains far smaller than a grain of sand. Those grains collided with each other. Some collisions destroyed grains, others let them stick together, forming slightly larger clumps. The larger clumps had slightly more gravity of their own, and so they swept up more material as they moved through the disk, growing larger still. Over a very long time, long enough that the word time stops carrying its usual weight, these clumps became the planets. And because every one of them grew out of material that was already moving in the disk, already orbiting the young sun in roughly the same plane, the planets inherited that plane. They did not need to be arranged afterward. The arrangement was built into how they formed. Anything that tried to grow somewhere outside the disk faced one of three fates. It could be pulled back into the plane by the disk's own gravity, settling in alongside everything else. It could be flung outward and lost entirely, scattered into the wider darkness beyond the forming system. Or it could simply never gather enough material to become anything at all, drifting as scattered, isolated debris rather than coalescing into a world. The disk that the planets grew within is gone now. Its remaining gas and dust were blown away by the young sun's first intense outpouring of light, billions of years ago. But the planets it shaped remain exactly where that disk placed them, in a thin, wide plane, all orbiting the same direction, all roughly aligned with one another, carrying the disk's geometry forward long after the disk itself disappeared. This is not a story unique to our solar system. The same physics, gravity pulling inward, rotation resisting that pulls sideways while allowing it along the spin axis, produces flattened, disc-shaped structures wherever it has the chance to act. The rings of Saturn are a disk on a much smaller scale, made of ice and rock instead of planets. The Milky Way itself, the galaxy that contains our entire solar system, is a disk, vastly larger, but shaped by the same underlying principle. Gravity and rotation working together across a span of time and space that makes our own solar system's history look brief by comparison. A flat solar system, in other words, is not a strange outcome. It is the expected one. A spherical solar system, planets scattered in every direction with no common plane, would be the surprising result, the one that would require some unusual explanation. What we have, instead, is the ordinary outcome of a perfectly ordinary process, repeated at every scale, where gravity and rotation occur together. The plane that the planets settled into has a precise name. Astronomers call it the invariable plane, defined as the average of all the planetary orbits, weighted by how much angular momentum each planet carries. Angular momentum depends on both mass and orbital motion, and one planet in our solar system carries far more of it than any other. Jupiter. Because Jupiter is so much more massive than every other planet combined, its orbit pulls the invariable plane strongly toward its own. In a real sense, the invariable plane is mostly Jupiter's plane, with everything else averaged in around it. Earth's orbit, The orbit that defines the line we casually call up and down in everyday life. The orbit that the listener is, at this moment, quietly riding along, sits at an angle of only about 1.5 degrees from this invariable plane, a small tilt. Small enough that for most everyday purposes, the difference does not matter at all. And the plane of Earth's orbit, the one astronomers call the ecliptic, is treated as if it were the plane of the solar system itself. Most of the other planets sit close to this same plane, each with its own small tilt. Mercury, the closest planet to the Sun, leans about 7 degrees away from it. The largest tilt among the major planets, though still a fairly gentle one. Venus and Mars and the outer gas giants each carry their own small variations, none of them dramatic. Pluto is the exception that tends to get mentioned, sitting at roughly 17 degrees from the plane, enough that its orbit visibly rises above and dips below the others, rather than lying neatly within their shared band. Beyond Pluto, a scattering of small icy bodies tilt even more steeply, and now and then a comet arrives from a direction with no relationship to the plane at all, plunging through it and out the other side before vanishing back into the distance it came from. But these are details at the edges. The overwhelming majority of what orbits the Sun, the planets, their moons, the asteroid belt, the bulk of everything we have ever sent a spacecraft to study, lies within a thin, shared band of sky. A band so consistent, so reliably narrow, that for the entire history of human observation, nobody needed to ask why the planets all moved along the same line. They moved along the same line because they were born from the same disk. And the people who first made real use of that line, who turned it from a curiosity into something they depended on for their lives, were not astronomers in observatories. They were sailors, far from land, reading the sky the way you might read a familiar road in the dark. The Pacific Ocean is the largest connected body of water on the surface of the Earth. Crossing it in vessels built from wood and woven fiber, without compasses or charts in the form we would recognize today, required a kind of relationship with the sky that most people today have never had reason to develop. Polynesian and Micronesian navigators built systems of wayfinding so precise that a star's rising point on the horizon could function as a compass bearing, and its height above the horizon at a particular hour could give a rough measure of how far north or south a vessel had traveled. The stars these navigators relied on most heavily were not scattered randomly across the sky. Many of them sat along or near that same shared band, the ecliptic, the disk seen edge on, because those were the brightest, most reliable, most consistently positioned points of light available. While a navigator did not need to know that this band represented the plane of the solar system. They needed the star to rise where it was supposed to rise, night after night, voyage after voyage, and it did. For 1,000 years of voyages across the Pacific, this band of sky, without ever being named as such, was trusted the way you trust a path you have walked 1,000 times. Not because anyone had explained why it worked, because it had never once failed. The disk was there before any of this. It was there before the first navigator ever looked up, before the first farmer ever timed a planting by the moon, before the first child ever noticed a strange pale glow after sunset and filed it away without a name. It has been there, quietly holding its shape for 4.5 billion years. What none of those people could see, what nobody has ever truly seen, is the disk from the outside, from above or from below, from the one direction that the disk's own geometry makes almost impossible to reach. That is where tonight's journey is headed next. Not into the disk. We have lived inside it for as long as we have existed. Out of it. And the reason that direction has remained so completely out of reach has nothing to do with distance. It has to do with how fast we are already moving and which way. Right now, without doing anything at all, you are moving at roughly 30 kilometers every second. Not the room you are in, not just the building or the city, or even the planet beneath you considered on its own. The entire Earth, every ocean, every mountain, every person on it, the atmosphere wrapped around all of it, is sweeping sideways around the Sun at a speed that would carry it from one side of a small country to the other in the space of a single second. It happens so smoothly, so constantly, that there is no way to feel it, no wind, no sense of motion, nothing pressing you back into your seat. The motion has been going on at essentially this same speed for the entire history of the Earth, and every living thing that has ever existed has experienced it as simply standing still. This is the detail that makes leaving the plane of the planet so much harder than it sounds. When a rocket lifts off from Earth's surface, it does not start from rest. It starts already carrying that 30 kilometers per second of sideways motion around the sun, inherited automatically the moment it leaves the ground, because the ground itself was already moving that fast. The rocket's engines do not need to create this motion. They only need to add to it or redirect it, depending on where the mission is headed, to reach orbit around Earth itself, the kind of orbit that satellites and space stations use. A spacecraft needs to add roughly 8 kilometers per second of additional speed relative to Earth's surface, on top of what it already has from the planet's own motion. To leave Earth's orbit entirely and head toward the Moon, a little more is needed, perhaps 3 or 4 kilometers per second beyond that. To reach Mars, using the kind of efficient path that takes advantage of where the planets happen to be in their orbits, the additional cost is around 4 kilometers per second beyond Earth orbit. To reach Jupiter, with or without help along the way, the cost rises to roughly 6.5 kilometers per second beyond Earth orbit. These numbers might sound large in isolation. They are not. They are well within what modern rockets, refined over 7 decades of practical engineering, can deliver, provided the spacecraft itself is not too heavy, and provided the mission is planned with enough care. Now consider a different kind of journey, not outward toward Mars or Jupiter or the icy edges of the solar system, straight up or straight down, perpendicular to the plane that every planet, every moon, every spacecraft humanity has ever launched has shared since the beginning. To do this, a spacecraft cannot simply add speed in the direction it is already moving. It has to cancel out the 30 kilometers per second of sideways motion it was born with, all of it, and replace that motion with an equivalent amount in a completely different direction. A direction that points up, out of the disk, into the open dark above or below it. The cost of doing this is roughly 30 kilometers per second of what mission planners call delta V. The total change in velocity a spacecraft is capable of producing using its engines and whatever fuel it carries. Sit with that number for a moment next to the others. Reaching Mars costs about 4 kilometers per second beyond Earth orbit. Reaching Jupiter costs about 6.5. Climbing perpendicular out of the plane to a height no greater than the distance from the Sun to the Earth, simply straight up rather than straight out, costs about 30. The largest interplanetary missions ever flown, carrying as much fuel as their designers could fit, while still leaving room for instruments and structure, have managed total delta V budgets, somewhere in the range of 15 to 20 kilometers per second across their entire operational lives. And most of that has been spent slowing down to enter orbit around a destination, not on the journey itself. A direct climb out of the plane is not slightly beyond what we can currently do. It is roughly twice what the most capable spacecraft ever built have managed, spent in a single direction, for a destination that, measured in pure distance, is closer than Pluto. This is one of the strangest facts in all of spaceflight, and it is worth letting it sit for a moment, because it inverts something that feels like it should be obvious. In ordinary experience, farther things are harder to reach than closer things. Pluto is far. The space directly above the Sun, at a height equal to Earth's own distance from it, is, in terms of raw distance, much closer. And yet reaching Pluto, for a spacecraft that has already been built and launched, is the easier of the two journeys, by a wide margin. The reason comes down entirely to geometry, to the difference between moving with something and moving against it. To travel outward, toward Jupiter or Saturn, or the distant edge of the solar system, a spacecraft does not need to fight its inherited motion. it can simply add a little more speed in the direction it is already going, widening its orbit gradually into a long ellipse that swings out toward its destination. The sun's gravity does almost all of the actual work of the journey, pulling the spacecraft along a curving path that the spacecraft itself barely needs to steer. A small push at the right moment, and the rest of the trip unfolds on its own. The way a ball rolled gently down a long slope will continue rolling on its own once it has been given that first push. To travel perpendicular to the plane, upward or downward, none of this help is available. The spacecraft's inherited sideways motion does not assist a vertical climb. It actively works against it. Every bit of upward velocity has to be created from nothing, paid for entirely in fuel, with no assistance from the existing motion and none from the sun's gravity, which pulls inward toward the center of the disk, not perpendicular to it. The plane is not like a road, where a traveler can choose to head in any direction with roughly equal effort. It is closer to a current, a wide, slow, powerful current that everything in the solar system has been caught inside for 4.5 billion years. Traveling within the current in whatever direction it happens to be flowing is easy. The current itself does most of the work. Trying to swim directly across it, perpendicular to its flow, means fighting the entire force of that current with nothing but your own effort. And the current, in this case, is the combined inherited motion of an entire planet. The poles of the sun, the regions directly above and below its center, where its axis of rotation would intersect its surface if extended outward, are, in this sense, more remote than the most distant icy world at the far edge of the solar system. Not because they are farther away, they are not. The sun's poles sit at roughly the same distance from Earth as the rest of the sun does. They are difficult to reach, because reaching them means stepping outside the current that gravity locked the entire solar system into, long before anything alive existed to notice. And yet, there is one way around this, one technique that has made nearly every distant mission of the last 60 years possible, and that offers, if used carefully enough, a path out of the current as well. It is called a gravity assist, sometimes a flyby, sometimes a slingshot. The idea is this: a spacecraft, traveling on a carefully chosen path, passes close by a planet, not landing, not entering orbit, simply passing through the planet's gravitational influence at a particular angle and a particular speed. As it passes, the planet's gravity bends the spacecraft's path, and depending on the geometry of that bend, the spacecraft can emerge from the encounter, moving faster, slower, or in a meaningfully different direction than it was moving before, all without burning a single drop of fuel. The planet, in turn, loses or gains an amount of its own orbital energy in exchange, an amount so small relative to the planet's enormous mass that it is utterly unmeasurable. The spacecraft borrows a sliver of the planet's motion. The planet does not notice. The spacecraft very much does. Jupiter is the most powerful gravitational slingshot in the solar system, simply because it is the most massive planet by a wide margin. A single carefully timed flyby of Jupiter can change a spacecraft's speed by 10 kilometers per second or more in one pass, and with the right approach angle, can redirect a spacecraft's path sharply out of the plane of the planets entirely. The fuel cost of this redirection is essentially zero. The cost instead is in precision. The spacecraft must arrive at exactly the right place, at exactly the right time, on exactly the right approach. Because once the encounter happens, the resulting path cannot easily be redrawn. The window for this kind of maneuver, once a mission is designed around it, is narrow, sometimes only days wide, for a journey that takes years to set up. Venus offers a gentler version of the same idea. Smaller than Jupiter, and so capable of only a small redirection per pass, but conveniently close to Earth, and available for repeated encounters. A spacecraft that loops between an inner orbit and Venus again and again can accumulate a small change in its orbital tilt with each pass, a few degrees at a time, climbing gradually out of the plane over the course of many years, rather than all at once. The process is slow. It is also, in terms of fuel, essentially free. The spacecraft pays in years of mission lifetime rather than in tons of propellant it does not have. Neither approach violates anything about how the solar system works. Energy is conserved in both cases, exactly as it always is. What gravity assists offer is not a shortcut around the laws of physics, but a way of using those laws, using the planets themselves and their enormous stores of orbital motion to accomplish what no spacecraft on its own could ever afford to do directly. This is, in the end, the only realistic path that has ever existed for climbing out of the plane. Not pushing straight up and paying the full impossible cost, using the planets as steps, borrowing motion from something far larger than anything we could ever carry with us, a little at a time, until a trajectory that began entirely within the disk has, almost imperceptibly, tilted its way out of it. 2 missions in the entire history of spaceflight have ever attempted this. One used Jupiter in a single decisive encounter to bend its path by nearly a right angle all at once. The other has been using Venus again and again, patiently, over years, climbing a little higher with each pass. The way someone might climb a long hill not by leaping, but by walking one slow step after another for as long as it takes. What each of them found once they reached the vantage point that no spacecraft before them had ever held is where tonight's journey goes next.